Hello everyone, welcome back to my channel. So in today's video we'll be seeing how to perform deletion operation in AVL trees. So in our previous videos we have seen how to perform the insertion operation, how to keep balancing the AVL trees. Now in this video we'll be seeing how to perform deletion in AVL trees. So I've already told this before and I'm saying once again that AVL trees is nothing but a binary search tree. So if you know the deletion in binary search tree, then the deletion in AVL trees is also exactly same. You're going to perform the same steps, and the only difference is that after deleting every node, okay, after deleting every node in the AVL tree, we have to check the whole tree if it is balanced or not. Okay, by checking the balance factor, we have to check if the whole tree is balanced or not. If in case it is unbalanced, then we have to balance it. So that's the only difference. So now let me show you how to delete in AVL trees. So I have jotted down the points for you. So these are some of the points that we need to take into consideration while deleting the nodes. The first thing is, if the node that you're deleting is a leaf node. Okay, if it is a leaf node, that is there are no children's attached to that node, then that means it is very simple, just delete that node directly, okay, without any hesitation. In case the node is having one child, okay, either left child or right child, any one side it can be. In case the node is having that child, then you're supposed to replace the node with that child and delete that node from there. Okay, so just delete that node and in place of that node put its child. Okay, that is the case in one child. Now suppose the given node is having two children, one on left side also, one on right side also. Now here comes the question, how to delete. Okay, so in this case you need to know how to write the in order for that. So you just have to see the in order predecessor or in order successor for that given node. Okay, and you need to replace that node with its in order predecessor or in order successor. What is in order predecessor? In order predecessor is the largest element of the left subtree, or you can say, yeah, that is for in order predecessor, and for in order successor it is the smallest element of the right subtree. That is how you find out the in order predecessor and successor. So you can take anyone, either predecessor or successor, and you can just replace that given node with this, and that's how you can delete it in case of two children. So here in case of AVL trees, you are supposed to delete like the nodes like this, and after deleting check for balancing. If it is unbalanced, then just try to balance the tree. Okay, so let me take an example over here. So I have my AVL tree present over here. I'm trying to delete the nodes. Now suppose I ask you to delete the node 5. Then it is very simple. You just have to remove this node from here because it doesn't have any child, right? It is a leaf node. So just delete it from there and that's it. The job is done. You just need to check for the balance factor. If it is unbalanced, balance it. So that is how you delete 5. Now suppose I ask you to delete 8 over here. So here comes the main question. Now 8 is having two children, one on left side also, one on right side also. So I'll just try to replace it with its in order predecessor, which is 5, or in order successor, which is 9. So you can replace with anyone. Okay, so let me replace it with its in order successor, that is 9. So when I replace it with its in order successor 9, 9 will come in place of 8, 8 will get deleted. So how will the tree look? The tree will look something like this. So here I have deleted 8 and this is what my tree looks like. I just replaced 8 with its in order successor, which is 9. Okay, now I told you in AVL trees, as soon as you delete the node, check for the balancing of the tree. So if you write all the balance factor, it comes as 0 and the tree is pretty much balanced. So there's nothing to balance over here. So now you can just move on and delete the other node that they have asked you to delete. Suppose I ask you to delete node 12. Okay, now I am asking you to delete the node 12. Now node 12 again has got a left child, right child, right? So now there is left subtree, right subtree. Now I need to check the in order for this. So either you replace 12 with its in order predecessor or in order successor. So what is in order predecessor for 12? I told you that the in order predecessor for 12 will be the largest element on the left subtree. What is the largest element on this left subtree? 9 is the largest element. So predecessor is 9. And what is the in order successor? It is the smallest element on the right subtree. So this is the right subtree, which is the smallest element on the right subtree. 13 is the smallest element on the right subtree. So the thing is, when you're trying to delete 12, you are supposed to replace 12 with either 9 or 13. It is your choice, whichever you want, you can replace with that number. So let me replace with the in order successor, because that is what I've been doing from starting. That is my way of doing it, my notion of doing it. You can replace with its predecessor, no issues for that. Now you can see I have replaced 12 with its in order successor, that is 13. So I just asked 13 to take the place of 12 and the deletion of 12 is done. Okay, so now after deleting, the next job is to check if the tree is balanced or not. Now again, if you write all the balance factor, it will come as 0, 0, 0, 0 for the bottom. Here it will come as 1. Here for 13 it will come as 2 minus 1, that is 1. Here it will be 0. So pretty much if you check the balance factor of all the nodes, it will be as 0, 1 or minus 1 only. That means the tree is balanced. Okay, the next thing that we're going to do is we're going to delete 14. So 14, if I delete, I just have to remove that 14 from there and the job is done. Okay, so let me just show you. Now I have deleted 14 simply because it was a leaf node. There was no child attached to it. Now after deleting 14, once again I need to check the balance factors. So the balance factor for the bottom ones are 0 because they are leaf nodes. For 9 it is 1 because 1 on the left side. And for 13 the balance factor comes as 2 because 2 on the left side and there is nothing on right side. So now that we have got an unbalanced tree over here. See, we know from the previous videos that if your balance factor does not lie between -1, 0 and 1, that means if the balance factor is not any of these three numbers, then your tree is unbalanced. You have to immediately perform rotations on it. And we have discussed about the rotations as well. So now you can see here we have got a number 2 as our balance factor, which means that this part of the tree needs to be balanced. Now how am I supposed to balance it? From 13 where you got 2, from that part you need to check. You need to check which type of rotation you have to perform. If you see, 9 is coming onto the left side of 13 and then 5 is coming onto the right, again onto the left side of 9. So you can see that the things are going onto the left side. Now since it is going onto the left side, what you're supposed to do, there are two LL. So when there is two LL, you're supposed to perform LL rotation. And in LL rotation, you're going to turn the whole part in clockwise direction. Okay, you will be turning it in clockwise direction. So what I am doing here is I am performing LL rotation, which is the clockwise rotation. So I'll turn this whole thing in clockwise direction. Okay, when I turn that whole thing in clockwise direction, my 15 will be as it is and right side part, that is 54, and this part. Okay, this subtree will be as it is. It will be attached over here as it is. There is no change for that. But on the left side, we are performing clockwise rotation. So 13 gets pulled down. 9 gets completely attached to this. 5 will be on the left side only. And 13 gets pulled down. Okay, so this is how you perform your clockwise rotation. I just turned this whole thing in the clockwise direction. And 9 gets attached to 15 directly. 13 will be pulled down. Okay, pulled down, and 5 will be attached as it is to 9. So this is how you perform your clockwise rotation. Now after performing clockwise rotation, if you check the balance factor again, you will get 0, 0, 0, and here too the balance factor will be same because that side nothing has changed, right? You have left it as it is. So balance factors are same for that side. And for overall 15, you have 2 on the left hand side and 3 as the height of right subtree. So 2 minus 3 is -1. So -1 is the balance factor of 15. So which means that the whole tree is pretty much balanced. So now you can see this is how you perform your deletion operation in AVL trees. So the deletion operation is very similar, in fact exactly similar to your binary search trees. The only change over here was after deleting each and every node, don't forget to check the balance factors and balance the whole tree once again. Okay, this is the only difference in the deletion of AVL trees and binary search trees. So that's all for this video. If you still have any doubts, you can let me know in the comment section below. Thank you for watching and meet you in my next video.